Good evening. Welcome to the RSCS member webinar series. I am Kim Hesselbarth, RSCS Marketing Manager. I would like to welcome everyone to tonight's session on troubleshooting reach-in coolers presented by Joe Marchese, CMS RCT. Joe's presentation will last approximately 45 minutes, and afterwards there will be a Q&A session. Please submit any questions that you may have throughout Joe's presentation using the GoToWebinar dialog box on the right-hand side of your screen. I'll field the questions and ask them aloud to Joe. Tonight's presentation is being recorded and will be available online for viewing at your convenience as soon as possible. Now I'd like to introduce our presenter for the evening, Joe Marchese.
Thank you, Kim. Okay, welcome everybody to tonight's presentation. Again, tonight's presentation is going to be on troubleshooting reach-in coolers, specifically those with capillary tube metering devices. We're going to focus...
I'm sorry, just to interject for a second. I do see your notes, so you might need to change it to the presentation slide, or the presentation.
Yes. Oh, thank you. Let me fix that. Is that better?
That's perfect. Thank you.
Oh, all right, no problem. All right. Sorry about that, guys. A little glitching on my computer side, but let's go ahead and get started. So again, we're going to focus tonight's presentation on reach-in coolers, and specifically those with capillary tube metering devices. So as we go through this program, kind of keep that in the back of your head that everything I'm discussing is on your generic reach-in cooler, no freezers, just coolers for this discussion, and those with capillary tube systems. Now, a lot of what we'll discuss can be applied to reach-in coolers that have a thermostatic expansion valve as its metering device. But when I get into some particulars, it's going to be focused on capillary tube systems. So let's go ahead and get started with that in mind. So the basic components of a reach-in cooler is pretty simplistic. There's not a whole lot of mechanical components. Now, I'm not saying it's always easy to troubleshoot them. They do have their challenges in how you go about accurately diagnosing a problem. But there's not a whole lot of mechanical components on these type of systems. You have your basic compressor condensing unit. Typically, it's going to be a reciprocating compressor, fractional horsepower. You're going to have usually a single circuited evaporator, sometimes multi-circuited evaporators, but for the most part, single circuited evaporators. We're going to focus on those systems with your cap tube metering devices, so that's a pretty simple type of metering device, but it has its complexity for sure. It has a basic temperature control, but one thing I want to make sure everyone is clear on tonight is that temperature control that we'll be discussing senses coil temperatures, not air temperatures. It's the way these systems generally operate is the unit is controlled by monitoring the coil or evaporated temperature. It's cycled on and off by measuring or the temperature sensor being attached directly to the evaporator. And there's a relationship between evaporating temperature and case temperature. And that's how these systems work. So keep that in mind. The type of temperature control that these systems use is coil sensing. And then the refrigerant, for the most part, medium temperature systems of this nature, you're going to see a lot of R134A systems. If you work on a really old system, original 12 system, you may see some blends out there that have been used to replace the 12 that was originally there, and you may even come across a R12 system that is still in existence. But it's been a while since 12 has been obsoleted, so most of the time it's going to be 134A that you'll be working on. The electrical side of these systems is also equally simplistic. It's not a whole lot to how they are electrically put together. But there are some important things that you should know going into troubleshooting these coolers from an electrical point of view that will help you out. One thing is the evaporator fan motor is designed to run all the time. It does not cycle on and off. during a defrost. It doesn't cycle on and off when the case gets the temperature. It runs all the time. If you look on the wiring diagram, the sample one I have on the screen, you'll see that there is no switching in the evaporator fan motor circuit. And that's good to know, because when you go up to the unit, when you're beginning your diagnosis of what the problem potentially is, you want to do a visual inspection, and one of the things you're looking for is the evaporator fan motor running or not. If it's not running, it tells you something that's happening, and if it is running, well, that's good. It's supposed to be running. Another thing that you'll see according to this wiring diagram is that the compressor and condenser fan motor are wired in parallel, meaning generally they run together. If the compressor is running, the condenser fan motor is running, and vice versa. Now, that's not always 100% true. I've seen some cases where the condenser fan motor has been wired to run all the time, either by design of a prior tech or by a manufacturer. So every once in a while you'll come across a condenser fan motor that runs all the time, and the compressor is the only thing that is cycling on and off by this temperature control. And you can verify that by looking at the wiring diagram to see if that's the way the manufacturer intended that system to work, or if a technician prior to you getting there rewired the system so the fan ran all the time. So watch out for that subtle possibility. Now, included in some of these electrical systems, you may see some lighting systems, general lighting system, lighting circuit, and every once in a while too you'll also see a defrost timer. A manufacturer will design their system to mechanically shut off the compressor by time to assist the defrosting of its evaporator. So you may see some wiring diagrams with a defrost timer inclusive in some of these regions. But what I'm showing you on the screen is by far the most common wiring scheme out there. So let's get into troubleshooting. And the number one reason for you being out there is going to be the case temperature is too high, right? You're going to get a call from a customer saying, hey, my case is too high, health department was just in here and it's supposed to read less than 41, let's say, and it's reading 45, or it's at 50 or 60 degrees. That's pretty common of a call. But the reasons for a case temperature that is higher than normal can be very diverse. Now, what I've listed on the screen here is some of the more common, or the most common reasons why your case temperature could be higher than normal. And what we're going to cover tonight is all of these possible scenarios and how you can determine which one of these possible causes is causing this case temperature to be too high. We're going to talk about dirty condensers, which by far is a pretty common reason for failures of these systems. Whether the condenser being dirty is the immediate failure, or the condenser being dirty caused another failure, for example, a defective compressor. So we'll talk about dirty condensers and some of the things that you should be looking for. We'll talk about defective condenser fan motors, defective compressors, how to troubleshoot your starting components, talk about how to analyze an iced evaporator, what causes the evaporator to ice up, talk about some temperature control issues, refrigerant leaks, pretty common problem, plugged capillary tubes. One of the takeaways from tonight's presentation is hopefully you can determine the difference between a system that has lost refrigerant or has a plugged cap tube. Opposite, opposing problems, but look similar at times when you're troubleshooting. So we're going to focus in later on tonight on talking about plugged cap tubes versus loss of refrigerant. Then we'll talk about evaporator fan motor failures and door hinges, door gaskets, the hardware side of things that could also cause some problems. So before we get into particulars, there is another possible reason for you to be out there, and that is not as common as an issue, but it's possible where the case is just too cold. For whatever reason, the case is too cold, and that's pretty common on salad coolers, produce coolers. They may complain of the tomatoes freezing or the lettuce freezing, and those problems are usually the result of a defective temperature control, problem with the temperature control, or the temperature control being set too low, or it could also be a slight loss of refrigerant. A very subtle loss of refrigerant may cause the temperature sensor on the controller not to see the right coil temperature, causing the unit to run longer than it should, dropping the case temperature below normal. So we'll talk about some of those issues as we go through tonight's program. There are some precautions that you want to be aware of when you're working on these type of systems. And it's actually a pretty serious precaution that you want to be aware of. Most of the time when you're working on these reach-in coolers, you're going to have to slide the condensing unit out from a cabinet or out from a cavity. Sliding it out, generally not a big deal. Every once in a while you're going to have to slide it out and then prop it up somehow, because it's going to be on rails where you don't want the condensing unit kind of hanging down. So be prepared to, when you slide it out, maybe have something to put underneath the condensing unit so it stays pretty level. Others you could slide right on onto the floor and it stays relatively level. So be concerned about how you pull it out and keeping it level. But the more serious concern, and something that you really have to be on the lookout for, is when you push it back in, especially on older units. And you're going to be working on a lot of older reach-in coolers, because that's the ones that are going to fail more commonly. And what you want not to happen is for the line set, either the liquid line or the suction line, to be damaged by you pushing back that condensing unit back into its cavity. And it can, and it does happen. It has happened to me, I hate to admit it, more than once, several times in my lifetime, and it's never a good scenario. One time I was working on a cooler, had it all fixed. I changed the compressor out and everything was perfect. I had the unit outside of its cavity. It ran like a champ, and as I was pushing it back in, I just kinked the suction line and caused it to crack, and all the refrigerant dumped out. I heard that magic hissing sound that you never want to hear as you're pushing it back, and I had to take it out, repair the suction line, re-evacuate the system, recharge it. All extra time and materials that was my error, and I could not charge the customer. Recently, I was working on a cooler, a beer cooler, where the same scenario happened to me, but I didn't realize the problem until the next, actually 2 days after the fact. And I had pulled out a condensing unit for a beer cooler, and just to change the condenser fan motor. So it was a fix, simple fix. Pulled out the unit, changed the condenser fan motor, pushed it back in. It was in a bar, pretty loud, pretty crowded. I didn't hear the magic hiss, but apparently when I pushed the unit back into the beer cooler, the suction line gave free, all the refrigerant dumped out. I didn't realize it at the time. I pushed it back in, took off. The next day they called up and said the cooler stopped working that night. Unfortunately, I couldn't get there until the next following day, so it was 2 days. The unit was kind of down, and it had dumped all the refrigerant out, and the compressor failed because it was running. It was an older compressor running without any refrigerant for 2 days. They did not unplug it, and the compressor failed. So I had to change the compressor and fix the leak, or for something, you know, maybe it was going to be avoided by how I pushed it back in. Now I did come to realize that it wasn't how I pushed it in that caused the problem. The suction line had a rub out already started, and I just aggravated the situation by pushing it back in. Luck of the draw is that I pushed it back in and it gave free. In any case, be cautious anytime you're pushing the condensing unit back in or taking it out of its cavity. You may create other problems that you were not there originally for. Another precaution is, since these units hold small amounts of refrigerant, I would recommend initially when you're doing your troubleshooting not to use manifold sets with long hoses, you know, like 3-foot or 6-foot hoses. That may cause enough refrigerant to be released just by you checking the pressure to cause the system not to work properly. So they do make, you know, stubby manifold, stubby pressure gauges that you can use. You can buy them at a wholesaler, or you can make up your own little stubby set. And that is definitely the way to go when you want to just measure pressure. If I want to measure the suction pressure or the discharge pressure of these units, I would recommend to use a short stubby gauge set for troubleshooting. Later on, when you have to fix something, you have to charge it and evacuate it and add refrigerant back in, then you're going to have to use your typical manifold set with the longer hoses, but that's okay because then you're adding refrigerant and you can compensate for any loss that you may have with your hoses. But during the troubleshooting part, using a stubby pressure gauge is definitely the way to go. So let's talk about your first steps when it comes to troubleshooting, and then we'll dive into these particular problems that you can run across. I find it's really good when you're doing any type of troubleshooting is to go into the job open-minded, first of all, clear mind. Don't think of every problem being the same. You got to go in there thinking clean slate. What's this problem? You may have just come from a plugged capillary tube system or something that had a defective compressor, and though this new job that you're on may look similar, it's probably not the same problem. So try to go into every job with an open mind, fresh slate, treat every unit as it's being unique. And I typically don't go in with any tools in hand at first. I'm the guy that goes in with a flashlight in hand, meet the customer, greet the customer, find out what the problem is, and then do a good visual inspection of the equipment that you're going to be working on. Look for the obvious, and generally, a lot of times, the problem is going to jump right at you just by a visual inspection. Not all the time, but sometimes. You look at the condenser. Is the condenser dirty? Look at the evaporator fan motor. Is it running? Because it's supposed to be running all the time. Is the evaporator iced over? Is the gaskets falling apart? Are the door hinges damaged? Look for the visual problems that could cause you and your customer some grief. Don't make any upfront decisions. Just look. Spend 5-10 minutes just looking around. Pull the cabinet out from its, a lot of times the cabinet's going to be in a food lineup. Pull it out, look behind it. A lot of times you'll see a plastic baggie right on the condenser. It's sucked in, not wax paper, but a plastic bag sucked in and blocking the condenser. It's a quick fix. Pull the bag out and the unit probably starts running okay. Or you find a really plugged up condenser. Wipe it down. Hopefully the dirty condenser didn't cause the compressor to fail. You won't know that until you at least clean it and try to run that system again. But a visual inspection, definitely the way to go. Once you do that, then you go out and get your tools and start the process. So let's talk about the very common, probably one of the most common reasons for failures is dirty condensers. Pretty routine. And you would think in a kitchen, in a food service environment, that it would take a lot for condensers to get dirty because it's a clean environment, but that's not true at all. They get pretty plugged up pretty bad. And how you clean them or the method of cleaning these does need some consideration. There's two scenarios you're going to run across when you're looking at these condensers. One is going to be dirt, like I'm showing you on the screen here. That's going to be pretty simple for you to clean up or clean. But sometimes in a really greasy environment, if it's in a food lineup next to a fryer, these things can get impacted with grease, and that's pretty problematic, and that's pretty difficult to clean. And sometimes you're not going to be able to do a good job cleaning them because the grease is rock hard. And there have been some occasions where it might be best practice to just change out the whole condenser or condensing unit if the compressor failed, because you just can't clean the coil. So you got to see what type of dirt you're dealing with. Is it grease, hardened grease? That's problematic. Or if it's just something that could be, brushed off. Now, when you're dealing with just dirt, like I'm showing you on the screen, word of caution, don't blow it out with compressed air or nitrogen. And that doesn't work. That works great. Compressed air or nitrogen will clean those condensers really well. But the problem you're going to have is that it's going to kick up a dust storm. And if you're in a kitchen and you blow these out with compressed air or nitrogen or something, and that dust cloud will go all over the kitchen, you're going to make some chefs, some cooks, very mad, because now they're going to have to clean all those surfaces off. And believe you me, I've done it. I've made some, not enemies, but I made some very people mad at me because I cleaned the condenser really well. I fixed the problem, but I made a dust storm in that area of the kitchen. So what I found is best is to brush them down. You know, brush in line with the fins. Take a decent brush. Doesn't have to be a real hard brush. It could be a pretty firm but soft brush, if you know what I mean, kind of like a strong nylon brush, and wipe it down, brush it with the fins, and get the dirt, rid of the dirt that way rather than blowing them out. You can also use some coil cleaner. They make some really good coil cleaner in a can that is rinseless. You apply it and you don't have to rinse it with water. So you can use that for these condensers, and they're pretty effective. These rinseless chemicals that you can use do work well. They even work somewhat okay on grease, depending on how impacted the grease is. But for dirt, they definitely do a good job. And grease, so-so. But you can definitely, and I use it a lot. I use these chemicals, rinseless chemicals. The only issue with them is that they pretty pungent. They smell. So you got to give a heads up to the people in the kitchen that you're going to use a chemical that has a pretty strong odor to it. May be offensive to some people, but it's definitely better than kicking up a dirt cloud by using compressed air. So you could spray this chemical on. What I normally do is brush it first with a good brush, get all the heavy dirt off, shut the unit off. Generally I don't apply the cleaner with the unit running. Shut it off, spray it down, leave it set up for maybe 5-10 minutes and plug the unit back in. And if it's really not that dirty, that is a pretty good effective way of cleaning those coils. Now I've also have on the screen there a filter, a sample of a picture of a filter, a fiberglass filter or even a mesh filter that guys put on condensers. And honestly, I'm kind of in between on this, if this is a good approach or not. I don't have any empirical data on whether or not this adversely affects the airflow through the condenser. So bearing that aside, let's assume that it doesn't affect the airflow through the condenser, and that part of it is okay for now. If you push that to the side, that is actually a very good technique to use then to keep these condensers clean. Easy cleanup, pull it out, put a new one on, so that's very nice. It does make you have to go back on a regular basis to clean them because these do get plugged up more frequently than just the coils. So you got to tell your customers, if you're going to go to this approach, I do need, or somebody needs to change these on a regular basis because they will plug up faster and lead to a loss of airflow more quickly than if you didn't have it on. But if you do keep up on the maintenance, it's a quick cleanup, right? Change it out, put it on. So I like it from that point of view. Does it affect the airflow? Honestly, I don't know. I've used them. I've seen them on units I've been on that I started doing maintenance on, and other companies have been using them in the past, and I've left them on, and I personally have not had problems with having them on. So, but I don't know that for a fact. If you guys know for a fact, you have data showing they're good or not, maybe at the end of this presentation you can send us a comment about that, because I've used them and not used them, but they're out there. I mean, an ice machine manufacturers use them all the time, so that's pretty common on ice machines to have these filters on their condensers. But on reach and coolers, I've seen them added on by techs. All right, let's move on to troubleshooting a fan motor, condenser fan motor. That's pretty simple. It's typically a shaded pole motor of some type. It's either going to run or not. They can fail electrically or mechanically. Electrically, an open winding, you'll find that with an ohm meter. If generally, if your compressor's running, your condenser fan motor has voltage to it, so if your compressor is running and the fan is not running, you got a bad condenser fan motor and you got to change it out. So that's what I kind of normally see. Condenser runs for a short period of time and it'll cycle off on its overload, but the compressor runs, fan doesn't. Chances are I'll be changing out that fan motor. And normally they fail mechanically rather than electrically. The bearings inside bind up, so you can't spin them, and you could tell that very easily by you try spinning it by hand and it's very tight. If you can't spin it by hand, change it out. When you change it out, remember to get the right condenser fan motor. They are spec'd by obviously voltage, by wattage, not necessarily horsepower, but by wattage. You'll see them rated at either a 2 watt, 4 watt, 6 watt, 9 watt, 16 watt. So make sure you match up watts for watch. And rotation. Clockwise is not always clockwise. Sometimes clockwise is counterclockwise, depending on how the manufacturer looks at their motor or rotation. Are they looking at the rotation looking at the shaft end, or are they looking at the rotation from the lead end? If you're looking at the shaft end and it's clockwise from viewing it from the shaft end, well, it's counterclockwise looking at it from the lead end. So depending on your motor manufacturer, that's kind of tricky sometimes. What you think is CW ends up being CCW on your replacement motor. So verify that, and if you're using a non-OEM fan motor, make sure your replacement has the right rotation, and be certain not just to go by clockwise or counterclockwise. Make sure they're looking at it from the same orientation. All right, let's talk about defective compressors. That's pretty common. You're going to come across these units that have a compressor that is giving you grief, and that's causing the case temperature to be hot. Compressors can fail either mechanically or electrically. We're going to talk about how to determine which is which. Here's a quick way of starting the process of knowing that your compressor is part of the problem. And what I normally do is I take my ammeter and I'll put it on the common lead, one of the electrical connections leading up to my compressor, and I want to measure an amperage. And the reason why I do that is sometimes you're in an area where you can't hear the compressor whether it's running or not. You may be in a bar, you may be in a busy, loud kitchen, and you may not be able to hear whether the compressor is actually running or not. So a good visual indication of whether it's electrically energized would be measuring its amperage. And that's generally pretty easy to do. Generally you can clamp on to one of the leads and see if it's consuming current. If it's consuming current, it's running. I'm not promising it's running right, but it's running. And then the next test is to touch the discharge line. If it's running, touch the discharge line. On a normal operating system, that discharge line should be well above room temperature and even a little hot. So don't grab a hold of it. If your ammeter shows it's drawing some current and the discharge line is room temperature, you got a problem. Whether it's the compressor is the problem, a loss of refrigerant's the problem, a plugged capillary tube, you got a problem. But I know I got a problem, right? I'm measuring current, my compressor's running, my discharge line is room temperature. Well, maybe a little bit above room temperature, but it's not hot. Now it's time to dive into the system a little bit more detail. Now you might think about, well, you may need to put your gauges on, put those stubby gauges on to see what the problem is. Is it loss of refrigerant? Is it a compressor that is not pumping? Or is it a plug cap tube? But at least I know I got a problem that I'm going to have. I got a serious problem here because my discharge line is really not warm at all, or not hot, and my compressor is consuming current. It's running. So that's my usually first test. Now, if your compressor starts but doesn't pump, so it's drawing current, my ammeter is telling me I'm drawing current, and my discharge line is room temperature. It could be that the compressor is not pumping, or it could be a loss of refrigerant. So I'm going to put my gauges on, right? And what I normally do is I unplug the unit first, stop the compressor, and I'm going to go ahead and put my gauges on. Now I'm going to normally have to put on a saddle valve. A lot of these systems are sealed systems that have never been, that don't have valves, access valves on them, unless they've been worked on before. So you're going to have to maybe put on a saddle valve to measure your pressures. When you do that, I'm going to recommend that you measure both your suction and your discharge pressures. A lot of guys just troubleshoot by looking at the suction pressure and not the discharge pressure, and that could lead you down a very dangerous hole or approach. Your suction pressure is not the only thing you need to be looking at. If you want to troubleshoot these units properly, look at both suction and discharge pressures, and that will avoid you making some common mistakes that we'll talk about coming up. So disconnect take the voltage away from the compressor, put saddle valves on if you have to, put both high and low side gauges on, and when you put your gauges on, one of the first things I'm looking for with the compressor not running is what my pressure is. If I'm not at my saturation pressure, in other words, for 134A, if it's a 70-degree ambient, 70 degrees surrounding temperature, I would expect the standing pressure to be around 71 pounds, right? But if I put my gauges on, compressor's not running, and both my high and low side read 20 pounds of pressure, or 10 pounds of pressure, or 30 pounds, or 40 pounds of pressure, I've lost a significant amount of refrigerant, and that's part of my problem. Maybe not the only problem. You could have a bad compressor still, right? You could have lost the refrigerant, and that caused the compressor to fail. So just because you've identified the loss of refrigerant, it doesn't mean that's not the only problem. So the next step is you plug the compressor, you turn the unit on and see what happens to your pressures, even though they're low at this point, right? And you know that it's lost refrigerant, so that's part of the problem. But you still want to see if that compressor has the ability to pump. So you plug it, turn it on, and you want to see your low side pressure drop and your high side pressure go up. Now I can't tell you where they should go because the pressures are going to be wrong, but you want to see a change, right? Low side pressure drop. Typically it's going to drop into a vacuum or very low, and your high side pressure is going to go up a little bit, but maybe not a whole lot. So that tells me that the compressor does pump, hopefully well enough to keep working, but at least it pumps, and my major issue at this point is just loss of refrigerant, which means I have a leak somewhere and I got to find the leak. If your pressures don't change, you start it up, measuring current, it's drawing current, compressor's running, but the pressures don't change or they change very little, you got a bad pump and a leak. You got two scenarios going on, and that is not uncommon. It is something that you may find where a loss of refrigerant caused the compressor fail, and you got two things to deal with. If your compressor cycles on the overload, it could be the result of a defective electrical component like a relay or capacitor. It could also be a mechanical failure where you got a lock rotor, and we'll talk about how to decipher between those two, whether it's a relay or a capacitor issue, or simply a mechanical lock inside, your rotor's locked. If the compressor doesn't start at all, no hum, it's just dead, it's probably an electrical issue, whether it's no voltage applied, you have no voltage to the compressor, or you have an open winding, right? So that could cause that electrical failure. Open winding or no voltage would cause the compressor not even to try to start, no amperage draw, no nothing. When you come across a compressor that doesn't start, no hum, no try, no amperage draw, first thing to do is to check to see if you have voltage going to the compressor. And I would recommend you go right to the compressor terminals, check between common and run, and seeing if you have 110 volts, whatever the nameplate voltage is. Typically 110 on these smaller regions. If you don't have the voltage, then you have a problem before the compressor. And don't overlook the overload as a possible reason why you don't have any voltage at the compressor. It could be a broken wire, or it could be a defective temperature control. It could also be the overload. overloads can fail. Not very common, but it's possible. So you can go across the overload on an energized circuit. If you read 115 volts across the overload on an energized circuit, that overload is open. That's the reason why the compressor is not on, perhaps. Or you can disconnect the voltage from the compressor, do a resistance check across the overload with one lead pulled off. Pull one lead off of the overload and just go across the overload with an ohm meter. And if you read continuity, the overload is good. If you read an open circuit, the overload is bad. You can also look at the overload. Flip the overload over. It has a bimetal disc on the inside. If you take the plate off, there's that tan plate I'm showing you on the screen. With a small screwdriver, you can pry that off, and you can look at the bimetal disc inside. If you see that it's cracked, bad overload. If it doesn't look bad, still do a resistance check on it or still do a voltage check on it, and it'll tell you if the switch is made or not. If you have voltage applied to the compressor and it's still not turning over, it's not consuming any current, it's not even trying to start, then you may have an issue with the windings inside. So now the next step is to do a resistance check on your compressor terminal leads. And you do that by measuring all three combinations. You go from common to run, common to start, and then run to start. And what you're really looking for is not absolute numbers, but a relationship. What you want to see is between common and run, that's your lowest resistance. Common to start, that's your next highest resistance. And then between run and start, you want to see the sum of the prior two resistances. So common to run, common to start should equal run to start. That's a good relationship. If you don't have that relationship, you've got a problem inside the compressor. Now here's a little trick you could use to identify these terminals. Most of the time the terminals are identified on the cover plate of the compressor, but let's say it's not. I can't promise you that this works all the time. It's not 100% across the board effective on all compressors all over the world, but on a lot of reach-in coolers made in the US, general coolers that you see from the popular manufacturers, this pin configuration is pretty common, at least as a starting point. So if you remember CSR, and read it like a book, top to bottom, left to right, and that will identify your common, start, and run terminals. CSR, reading it like a book, top to bottom, left to right. On a lot of these reach-in coolers, that would be a pretty common pin configuration. But don't hold me to it. I can't tell you every compressor manufacturer out there in the whole wide world follows that same pattern. But a lot of the ones that I've worked on do. A couple other things to look for, not real common, but you can come across a shorted winding. If at any time when you're measuring these three resistances you find a true zero resistance, where it's really zero, all three combinations, you find one combination or two combinations that have a true zero, that's a shorted winding, bad compressor. But more common, it's going to be an open compressor, an open winding. And when you do these resistance checks, you'll find that one or two combinations will give you an open resistance, an overload, or an infinite resistance value. Now, word of precaution, when on some of the new meters that we've been using, some of the new ohm meters and multimeters that are out there can read in the millions of ohms range. And don't let that fool you. If you may read a couple of million ohms between an open winding, and that gives you a number on your meter, and that number may elude you to believe that the compressor is okay, but it's reading 2 million ohms, and that's not good. If you read 2 million ohms across common to run or common to start, that's not good. But if you don't see that little M on your meter, you're in a dark location, remember sometimes you're working upside down and backwards on a floor and not in a very best lit area. So you may overlook the little M on your meter, meaning you're reading in the million ohm range. Don't let that fool you. It's fooled me, so I can only imagine it's fooled some other people as well. what I've gotten into the habit of doing on my new meter is I manually select the range. I know I'm working on a compressor that's going to have low resistance values, so I manually select where it's reading in ohms, not in kilo ohms, not in million ohms, not in anything, but just ohms. And now I won't make that mistake because it says OL on my meter. I know it's an open circuit and I'm not making a mistake. So watch out for that on some of the newer meters that can read pretty high resistance values. And while you're at it, you can also do a quick check for ground. Generally, if it's grounded, you would have known it by now because every time you plugged it in, it would have blown a circuit breaker. But while you're doing this resistance checks, do a quick check for ground. Go from the body of the compressor, usually go from the suction stub, connect to the suction stub with one of your leads, and then go to all three terminals, and you should read infinite resistance from any terminal to ground using your standard ohm meter that's not reading millions of ohms. Get away from the million ohm meters because you may read millions of ohms from any terminal to ground. That doesn't mean it's shorted. It's just a high resistance value. So get away from these million ohm meters when you're doing these tests. They really can cause you some grief. Kim, I think it's time for a poll question. If you want to go ahead and launch that.
All right, thank you, Joe.
Okay.
And that question is, which of the following is the most common cause of a failed reach-in cooler? Is it A, dirty condenser, B, defective start capacitor, C, plugged capillary, or D, defective evaporator fan motor? If you would, please go ahead and place your votes. And we'll leave it open just a few seconds longer here so people can finalize casting their votes, and then we'll share the results with everyone along with the correct answer. All right, and it looks like most people have done that, so we'll go ahead and get it closed. And the correct answer is A, dirty condenser, and 95% of the people answered that correctly.
Perfect.
Back to you.
Okay, do I have to do anything on my end? No, I'm good, right?
No, you're good.
Okay. All right, so another possible reason why a compressor won't start is a defective start capacitor. And normally you'll see that by a visual inspection. These start capacitors have a vent plug, and if you see the vent plug blown out, bad capacitor. But you can also do a test with a capacitance meter. Measure the capacitance. It should be what the nameplate value is on the capacitor. If it's not, change the capacitor out. Try a new capacitor, and that generally will could solve the problem why the compressor is not starting. So if you have a compressor that's not starting, always make sure you check your capacitor and see if it's not the cause. If you ever had to replace the capacitor, make sure you put on a bleed resistor on the replacement capacitor, or make sure the replacement capacitor has a bleed resistor. If you put a start capacitor on without a bleed resistor, you could cause both the relay and the capacitor to fail prematurely. You want to use the bleed resistor to bleed the energy away from the capacitor every time that unit starts up. Without a bleed resistor, you'll get a little bit of arcing across the terminals of that relay, causing the terminals to burn out before it's time. So please make sure you put a bleed resistor on any replacement capacitor. If yours doesn't have it, you can buy resistors from your wholesaler that you can attach to your replacement capacitor. All right, let's talk about a relay. A defective relay can definitely cause you to have a compressor that doesn't start. The most common type of relay used on these type of systems is the current relay. So let me show you how the current relay operates first, and then we'll talk about how to troubleshoot whether it works or not. So the current relay is basically a relay that works off of the high inrush current that a compressor will see during startup. The coil of the relay is wired in series with the run winding. So the coil of the relay sees the same current as the run winding. And on startup, the current's going to be high and then drop off when the compressor starts. So the relay is designed to close on this high inrush of currents. When you first energize it, the inrush current being high, that lock rotor amperage being what it is, causes the switch of the relay to close. That brings in the start capacitor, brings in the start winding. That gives the compressor enough torque to get off of a dead start. The rotor starts to spin. As the rotor starts to spin, the current level drops. That current level drop causes the relay to open up again, dropping out the start relay, the contacts of the relay, and dropping out the start winding, and now the compressor operates just on the run winding normally. Knowing that, we could talk about how to troubleshoot it. When these fail, they're either going to fail bad coil or bad contacts. I can check the coil by measuring my resistance across the coil. Take the relay out of the circuit, de-energize the voltage, take the voltage down, take the relay out, measure the resistance of the coil. These coil resistances should be very low, less than an ohm, so very low resistance. If you read a very high resistance or an infinite resistance, the coil is bad. Generally, you're going to read the coil resistance from the L and M terminals of the relay. I can't promise you that's always going to be the right terminal identifications on every relay. So look on the relay and make sure you're measuring the coil resistance. And they all should be very low, typically less than an ohm. On the switch side, you want to measure across the contacts. These are weighted or positional relays. In their normal upright position, their relay de-energized, no voltage, no current present. The relay switch should be open. So you should measure an open circuit, an open switch with your ohm meter when you go across the switch. Then what you can do as a test is you turn it upside down. Since it's a weighted relay, when you turn it upside down, you can force the contacts to close. Turning it upside down, you should see the contacts close, and you should see that shown on your ohm meter. You should see zero resistance at this point. Sometimes you have to shake it when it's upside down. So you turn it upside down and you give it a shake, and you should see the relay switch closing. If it never closes, if you from upright to upside down and shaking it a little bit, the relay never closes, its switch never closes, it's a bad relay. Change the relay out, and that probably solves your problem. So that's how you check the switch. Upright position open, flip it over and shake it, it should close. Now there's going to come a point where you're going to doubt yourself, and you're going to say, I don't know if it's the relay. I did the test that Joe said, and I don't know, I'm not sure. Well, here's something that you can do that will proof positively tell you whether the compressor is good or bad and eliminate the starting components. And that's by using a hermetic analyzer. You can buy a hermetic analyzer where you directly connect this analyzer to your compressor, and it becomes your starting relay, it becomes your starting capacitor, and you use that to start the compressor. If you can get the compressor to run using this hermetic analyzer, the compressor at least electrically runs. If you can't get it to electrically turn over with your analyzer, it's a bad compressor, change the compressor out. So when in doubt, go to a hermetic analyzer. It's a worthwhile tool to have. It really allows you to be real confident knowing that the compressor is electrically good or not, or turns over or doesn't turn over. All right, let's talk about iced evaporators. Pretty common problem. Iced evaporators could be caused by several different reasons. Loss of refrigerant can cause an evaporator to ice up. A defective temperature control can equally cause it to ice up. It could also be caused by high uses in high ambience where the unit runs, never shuts off because they're opening the door, or the gasket, the door never closes properly, so it never ever seals the compartment so it can drop temperature. So a damaged door gasket, high usage in a high ambient, or particularly the temperature control that's just set too low. So those are some things that can cause you to have an iced evaporator, and we're going to talk about how you can define which is which. So you have an iced evaporator, you have to decide whether it's a loss of charge, temperature control issue, or just high ambient or bad gaskets. So the first step is you got to start with a clean evaporator, so you're going to have to defrost the evaporator. Can't troubleshoot it with a frozen evaporator in place. So the first things first, get rid of the ice. When you do that, be careful not to cause any damage to the evaporator. No hammers, no chisels, no hitting it, no scraping it, no banging on it, no torches, no, just get rid of it. Best practice is a heat gun. Low impact heat gun, get the ice away, very slow, be very careful not to melt any wires, melt any plastic cabinets. Be very diligent, very careful on how you defrost these coils. You don't want to create more work for yourself. Once you have a clean coil, then we can start to determine whether it's temperature control or loss of refrigerant, right? So a temperature control that causes an iced evaporator generally means the thermostat is stuck closed, right? So how are you going to determine that it's stuck closed? Well, a good way of determining that is to measure the temperature at the same location where the sensing element is connected to that evaporator. So put a thermistor, not thermistor, thermocouple, your thermocouple in the area where the capillary tube sensor for the temperature control is located. Usually it's in a well, so you can push it into the well with the sensor or next to the well. Somehow try to measure the coil temperature and run the unit. And then you have to determine at what coil temperature should that unit be shutting off. 20 degrees, 25 degrees. You're going to have to determine what is the right coil temperature for that unit to be shutting off at. If the unit drops below that temperature, let's say you look up the specs and it's calling for 25 degrees or 20 degrees, 20 degree coil temperature, that unit should be shutting off. And you measure 19, 18, 15, 10 degrees. It's getting down to 10 degrees and the temperature control doesn't open up. It's a bad temperature control. If you never get down to that setting, let's say 20 degrees, and let's say your coil never gets down to that setting, well, that's a problem. That's why the unit's never shutting off, because the coil is not getting to the right temperature for another reason. So you can segment whether it's the temperature sensor or system problem, or another system problem that's causing it to run too long. It's not easy to measure the coil temperature, so I'm not going to promise you that's always an easy task, but that is a really good approach. If you can measure coil temperature and run the system with a clean evaporator, you can determine whether it's truly the temperature sensor or not. That's one approach to definitely use to determine whether it's this temperature sensor, temperature control, or something else. If you determine it is the temperature control, well, remember it's a constant cut-in temperature control. Make sure you replace it with a constant temperature cut-in control, and make sure that when you can, use the OEM replacement. This way you're getting the right temperature range. They do make universal ones on the market that do work, but you got to make sure they work within the temperature range that you need it to work in. So you might have to do some research to find out what is the right universal one to work. But when in doubt, get the OEM one. It makes life a whole lot easier, and make sure you put the temperature sensor back in the same location that the original was at. Put it back in that well, which is not always easy, which is sometimes a chore all by itself. They don't make that easy, but that's the best approach. You'll come across some of these reach-in coolers that have digital temperature sensors, and the rules don't change because it's digital versus mechanical. So it's the same approach, it's just a different style of temperature sensor, but troubleshooting it is the same manner. All right, Kim, I sped it up there a little bit, so now we're ready for the second poll question, if you want to go ahead and launch that.
All right. And that question is, what type of starting relay is commonly used on a reach-in cooler? Is it A, potential relay, B, current relay, or C, general purpose relay? So if you would, go ahead and place your votes. And we'll give it just a couple more seconds for everyone to get those votes cast, and then we'll share the results and correct answer. All right, looks like most people have. And the correct answer is B, current relay. And we've got 86% of the people answering that correctly.
All right, thanks.
You're welcome. It's back to you.
Okay. All right, so now let's talk about how to identify a loss of refrigerant as being a reason why you have an iced evaporator or a case temperature that's too high. Depending on the amount of refrigerant lost, a nice telltale sign is the icing pattern on the evaporator. If you've lost a nice amount of refrigerant, but not all the refrigerant, so you've lost half of the charge, again, not the entire charge, but half of the charge, what you'll normally see is you'll have a very heavy amount of icing on the inlet side of the evaporator, and the icing pattern will diminish as it goes across the evaporator, so it's not going to be uniform. Now, depending on how long they've let the unit run this way, it can cover a pretty nice portion of the evaporator. But generally what you'll see is either a big ball of ice on the inlet side of the evaporator, or it's very, very, very heavy on the inlet side of that evaporator. And that's a pretty strong sign that it's a loss of charge. You'll confirm that with your gauges. Once you see that, I'm not saying stop the game there and diagnose it right there. Put your gauges on, measure high side and low side. Again, you're going to have to add a tapper line at times, but measure your high side pressure and low side pressure. And what you'll see with the system running, low side pressure, low discharge pressure. So if you have a low suction pressure and a low high side pressure with that icing pattern, low charge. That's it. Got to go ahead and find the leak. Be done with it. Now, when you put your saddle valves on, a couple of things to just be concerned about. One, make sure when you put it on the process tubes that you clean the process tubes. You don't want your saddle valve to leak. So sand it down, get a nice clean surface. Make sure you have a good metal-to-metal contact on your valve. Make sure you're not causing a leak. All right. And when you can, remove the saddle valves when you're done. Now you're going to say, Joe, how could you remove the saddle valves? That's retarded. I put a hole in it. How am I going to take the valve off? Well, there is a way of doing it, and I'll show you that coming up in a couple seconds. Once you determine that you have a low charge, then you're going to have to go and look for the leak. And there is nothing special about these units as far as leak searching. It's the common leak searching methods. What I use typically is electronic leak detector. Get me in the area, soap it up, and I don't fix the leak until I see it with soap bubbles. But I start off with the electronic leak detector. I look for oily areas, try to find the oil, try and use the electronic leak detector to say, yeah, I'm close, and then soap it up. And then either you fix the leak or you can't fix the leak. Just as a heads up, a lot of times these units will leak in the evaporator coil due to the acidity of the products being in the case. If you have a leak in an evaporator coil, best practice, change the coil out. You can try fixing the coils, but you might be chasing your tail. Sometimes you'll fix one leak and then another leak develops. You'll fix another leak and another leak develops. Sometimes it's best just to cut your losses and change out the entire evaporator if you find the leak is in the evaporator. It's not always in the evaporator, but it's pretty common in a lot of these cases. When it comes to adding refrigerant back into these units, best practice is weighing in the charge. Weighing in whatever the manufacturer told you the original charge should be, weigh that amount in. Forget about the superheat and subcooling approaches. It's very difficult to pinpoint those on these units. Weigh in the charge. If it holds 8 ounces, if it holds 9 ounces, if it holds 20 ounces, weigh that in and be done with it. Fix the leak, pressurize it, evacuate it, weigh in the charge, done. Best approach when it comes to these type of systems. Now here's taking off the saddle valves. Here's how you can take off saddle valves with a pinch-off tool. You pinch between the system and the saddle valve, and you double pinch it. One pinch, and then you take a second pinch and you hold it with your pinch-off tool in place. Take off the saddle valve, expose the hole that you made, braze it shut. Okay, you're holding refrigerant back with your pinch-off tool, but you're going to braze that little opening and then take off your pinch-off tool. And honestly, somebody, if they don't look close at it, can never tell that you actually touched the system because you've pinched it off. So it is possible to take off your saddle valves using a pinch-off tool on an operating system. It's extra work, but it's good practice because those saddle valves are not really designed for long-term use. They will leak over time. Maybe a year, 2, 3 years down the road, they will probably leak. So if you can take them off, you're doing your customer a great service. Do you have to take them off? That's your call. Would I recommend it? If you have the time and you can, absolutely take off the saddle valves. All right, let's talk about capillary tubes. Capillary tubes are pretty simplistic in how they operate. It's just a fixed restriction. But what is important is to determine whether you have a low refrigerant charge versus a plugged capillary tube. All right, so that's the issue. How do you determine whether it's a plugged cap tube or a lower charge? Both systems will show a lower than normal suction pressure. So if you're just looking at suction pressure and you'll see a low suction pressure, you're guessing at the problem. Yeah, a lot of times it's a low charge and you put refrigerant in and it'll work. But the tell is on the high side. With a plugged capillary tube, your high side pressure will be normal to slightly elevated. With a loss of refrigerant, it's going to be low. So your high side is the tell on whether it's a plugged capillary tube system or not. Low suction pressure is going to be low on both scenarios. It's your discharge pressure that's going to tell you the tell. When in doubt, because sometimes you're not going to be able to identify normal discharge to slightly low discharge, so you're not 100% sure. What you can do is weigh in, put a little refrigerant in, but weigh it in. Put like a couple ounces of refrigerant in and see what happens. If you put a couple ounces of refrigerant in, if you see the system starting to work normally, then it was a low charge. If you see your discharge pressure starting to creep up and your suction pressure is locked in, it's still very, very low or in a vacuum, and your discharge pressure is going up as you're putting more refrigerant in, stop. It's a plug cap tube. So you can add a little refrigerant and see what happens if you're not sure about the high side pressure. It is a waste of time and it's a waste of refrigerant, but it is another approach. But the high side approach normally tells you the difference between a plug tube and a loss of charge. If you have to change the capillary tube, best to get the OEM, but in lieu of that, you can get a general replacement. There are companies out there that sell generic replacements. The generic replacements need to be sized properly, meaning they need to be cut to length. So just follow the manufacturer's charts. Here's an example of a chart on the screen. This particular manufacturer tells you how many feet of capillary tube for a particular capillary tube size for a particular application. So basically follow the directions that these universal cap tube manufacturers give you and it'll work fine. But if you don't want to do that, get the OEM replacement. Defective fan motors, if you come across a fan motor that's not running, that's pretty easy to tell. The fan's not spinning. And generally what will happen, the unit will short cycle. It'll run for a little while, shut off on a temperature control. Since you don't have any air moving across the evaporator gets cold really quick, shuts off, comes back on, shuts off, comes back on. So you see this short cycling of the compressor, runs for maybe 2 or 3 minutes, is off for 2 or 3 minutes, comes back on, and there's no air across the evaporator because the fan's not spinning, so it's a bad fan motor. Verify it, make sure you have voltage going to the fan first, and then if you have voltage going to the fan and if it's not spinning, change the fan. So that's a pretty simple tell. Don't forget to look at your door gaskets, door hinges. If you don't have a tight compartment, you will not make temperature. That could cause a case to freeze up or not maintain temperature, so always inspect your door gaskets, make sure they're in good shape. A torn, ripped door gasket can cause you grief, and it's not a mechanical problem, it's a hardware problem. Same thing with a door hinge. A door hinge that's not making good contact can cause grief. Here is a quick test to test the integrity of a door gasket. It's a dollar bill test. Put the dollar bill between the cabinet and the door, and it should give you a slight resistance as you pull on it. If the dollar falls on its own or has no resistance when you pull it, the gasket is not good. You should feel a slight tug, slight resistance as you pull the dollar bill away from the space between the gasket and the door. And you need to do that on all 4 sides, top and bottom. You want to test all the sides and all top and bottom areas. And that makes sure that you have a good integrity on your door gasket. That could equally cause you to have a high temperature. One last thing before we call it quits. It's not a mechanical issue as far as causing temperature issues, but it is a common problem, and that's a water dripping from the case or water in the cabinet, and that's generally just a clogged drain. You got to clean the drain. Sometimes you have a rotted evaporator pan, and you have to change the evaporator pan, but generally speaking, if you have water in the bottom of a cabinet or on the floor leaking out of the cabinet, it's the result of a clogged drain. You're just going to have to get pretty creative in how you clean the drains. There's not one way that works all the time. You have to use a couple of different approaches. Just make sure you clean the drain. Otherwise, the problem won't go away. Kim, I apologize. I went a little over, but that concludes my presentation. So if you want to open it up for questions, or if you want people to send me questions, I'm open to either way.
We'll go ahead and take a few questions here, and then we'll wrap it up in just a few minutes probably.
Okay.
We do have an individual who is asking, what about using a vacuum to clean the coils?
Absolutely, yes. You can use a good vacuum. If it's loose dirt, you know, like dirt, not grease, a brush and a good vacuum cleaner will work, and then put some coil cleaner on it as kind of a finishing up process, and yes, that will work fine.
Okay. And then is there ever a reason to change the rotation of the condenser fan motor to blow through the condenser coil? Perhaps the environment calls for it. This particular individual said, I tend to think the tech before me left it that way on purpose, but maybe not.
Yeah, I've seen that too, and I've questioned the same thing in my head. I don't think it's right, because you want the air going over the compressor to cool the compressor too, a little bit. Most of the compressors are refrigerant cooled, but you do want the air blowing over the compressor as well. So I don't think it's the right approach to change the rotation of that fan to blow through instead of drawing through. Most condenser fans, you draw the air through the coil and over the compressor. To push it out, I don't think it's right. I've seen it. I don't like it. But that's a better question to a manufacturer than me, I would think. I wouldn't leave it that way.
Okay.
But we have to get true or beverage air input on that.
All right. Another individual said, I recently came across a 2-door cooler with a switch for the condenser fan in the cabinet next to the light switch. What application could possibly need to switch off the condenser fan with a switch?
None that I can think of, unless it's for the condensing unit, where they have a switch to shut off the whole condensing unit, and that would be for just if they have to clean the case out. But if the switch was just for the condenser fan motor, I can't think of any application where that makes any sense at all. That's stupid, actually, because if you shut the condenser fan off and run the compressor, that's just trouble happening. So if it's a switch for the condensing unit, well, that could just be for maintenance purposes. For the condenser, I don't think that's appropriate or right, actually.
Okay. What is the action that causes some products to rot the coils?
From what I've been told, it's acidic food products. Tomatoes, tomato paste, tomato sauce, any food that has a acidic component to it, it eats the copper away, and that's just the nature of the beast. What you'll see now is newer systems come with coated evaporators, where they put a coating over it to stop that from happening. So the new systems will have like a plastic coating around the evaporator coils to kind of help with that scenario. But I've been told the common problem is all based on acidic food products.
Okay. And can you use temp probes to troubleshoot if the unit does not have access ports?
Yes, and I did not mention that, but yes, you can. That is another effective way of troubleshooting. You can measure your temperature difference across your evaporator and your temperature difference across your condenser. Generally, an operating system, you should see about a 10-degree temperature difference across the evaporator and about a 20-degree temperature difference across your condenser. That's a good system. If your temperature is difference across the evaporator and the condenser is low, that's an issue with either a defective compressor or low refrigerant charge. So yes, you can use temperature drop across your coils as a means of troubleshooting. Absolutely.
Okay. Another person was asking, why sense the coil temperature instead of a box temperature with an air thermostat?
They do that for defrosting purposes. So these coils have to defrost, so they're kind of killing two birds with one stone. They're measuring the coil temperature so that when the unit shuts off, it stays off until the coil is defrosted properly, and then the unit comes on. So it's kind of a way of defrosting the coil on every off cycle. It's called off-cycle defrost for that reason, so that you defrost the coil and control the temperature with one component. If you just sensed air temperature, then you would also need some means of defrosting the coil on a regular basis, which would be like a defrost timer or another defrosting circuit. So it's a convenient way of killing two birds with one stone.
Okay. How common is a plugged cap tube on these R134A systems? Is this from the oil breakdown in the system?
Yes, I've been told that. I've been told that with the POE oils, when you have high discharge temperatures, when you have a failed compressor as a result of a bad condenser fan motor or a plug condenser, and you elevate the system temperatures and pressures to a point, the oil breaks down and it kind of creates a byproduct that does plug the capillary tubes up. So it's not uncommon for a service tech or a service company, when they have a failed compressor, to also automatically change the cap tube out just as a normal means of business. The cap tube may or may not be plugged, but they don't want to take that chance because of this potential problem with the POE oils kind of developing the plugging issue. So they just change both at the same time. The system's open, do it, get it done with, and they'll have peace of mind. But yeah, that is a common issue with POE oils and elevated temperatures.
Okay. I do have someone commenting on the condenser switch. That was a question just a few questions ago.
Okay.
They're making a notation that I thought would be applicable. They said on the beverage air unit, the condenser switch is to run the condenser fan motor constantly to keep the glass door from fogging in high humidity areas.
Okay, that's different than shutting it off. Okay, that kind of makes sense. Okay. Yeah, so you're running the condenser fan continuously, you're not shutting it off. That, yeah, I can buy that. That works.
And then another question is, what has to be taken into consideration when adding a hot gas discharge line into a drain pan to replace an electric heater drain pan?
Huh, interesting. Okay, so usually it's the opposite that you see guys doing, which is not right. You know, the opposite is common, where guys will take out the discharge line out of the pan and put in a heated pan, and that just causes them problems because you're going to be running elevated discharge pressures from that point forward. So don't do that. If you have a system that has the discharge line running through a condensate pan and you have an issue with a leak at that location, fix the leak, change out that line, but don't eliminate it running through that condensate pan. So the opposite definitely don't do, but to switch over from an electric condensate to a discharge line running through a condensate pan, that will your charge will be off, because you'll be adding more discharge lines, so you can't weigh in the charge accurately because you're not going to know 100% what the charge is because you're kind of repiping the system. So that'll be a little bit of a challenge, but your discharge pressures will be lowered. I've never done it, so I don't know what the end result will be.
Okay.
So, good question.
Are there pressure switches still used for temperature controls?
Yes, there are plenty of reach-in coolers out there that use a thermostatic expansion valve with a low pressure switch. Tonight's presentation was focused on capillary tubes, but that's not the only type of reach-in cooler out there. There's plenty of them with expansion valves and still use pressure switches for temperature control, but that's another discussion for another night.
All right, and we're going to go ahead and take one more question here, which is, with a plugged cap tube, will you see any temperature, any type of temperature difference from one side of the cap tube to the other?
Well, yeah, you would, even on a normally operating. So yes, you would see a temperature difference from the inlet to the outlet. I don't know what it should be, what's the right number. The problem with plug capillary tubes is there's different degrees of how they're plugged. You know, partially plugged, more plugged than not, less plugged, slightly plugged. So depending on how fouled up they are, you're going to get different temperature readings. So it's hard to give, probably it's hard to say what the exact temperature difference would be. A normally operating unit would have one temperature difference. A plug capillary tube would have a different temperature, but I don't know what the numbers would be.
Okay. All right. I'm going to go ahead and close it out for the evening.
Okay.
All right. Thank you to everyone for attending this webinar, and thank you to Joe for taking the time to present this topic. For those of you that would like to view this presentation at a later date, you can do so in the next few days on the members only section of rscs.org, which I can show you to how you can get there right now. So you will go to rscs.org, and then you'll type in your username and password. Select the login button. Once here, select the My RSCS homepage underneath the logout button, and then on the left navigation bar, select webinars. In the center of the page, upcoming webinars and archived webinars will be populated. Also, webinar attendees from tonight's live event should receive a certificate for completing 1 hour of continuing education within 7 to 10 business days. If you have any questions, you can email me at webinars@rscs.org. Again, that's webinars@rscs.org. Thank you again, everyone, for joining us tonight. Have a great night. This webinar is now concluded.